We're going to take a quick look at the issue of multicolinearity. It's basically when we have a high degree of correlation between our independent variables. When we were looking at our multiple linear regression for 3C, looking at repair hours and part costs, it might be that these two variables are highly correlated. Complex parts cost more, and perhaps complex parts cost more to install, and that these variables could tell us very much the same information. If that's the case, we would want to be careful including both of them in our linear regression model. I've put together some contrived data that has a high degree of multicollinearity. We're going to look at estimated regression models for two sets of data. One using repair hours here at 9,050, and the other one, I've changed that slightly to $89,080. In all other respects, these two sets of data are identical. We can look at the R-square for each of these coefficients independently. Both of them explain roughly 82 or 83% of our variation. For our model here on the left, our slope coefficient for repair hours is 12.5. Our slope coefficient for machine hours is 0.27. In other words, we're going to have an increase in cost of 27 or 28 cents every time we run our machines for 1 hour. We're going to have an increase in our overhead cost of $12.50 every time we spend 1 hour doing repairs. Now, for our other data set, we've got similar slope coefficients. Again, these are looking at them independently. And again, we would expect them to be very much the same because the only thing that changed was our machine hours slightly. What happens, though, if we include both of these models in a both of these independent variables in a multiple linear regression model? Let's first look at the repair output, or our cost estimates, regression estimates using the data set here on the left. What do we observe? The coefficient for repair hours now, instead of being $12.52 positive, it's now a negative 76. Look at the standard error, though. The standard error dwarfs the coefficient. So what's the probability that this is really a valid number and it's not zero? Well, look at the t-stat and look at the p-value, which basically this information is telling us that this estimate is pure garbage. There's a 90% chance that the real value is zero, and we just got 76 by chance based on the data we selected. If we look at the coefficient and the standard error for machine hours, we get something almost just as strange again. Independently, these had pretty good explanatory powers, but if we look at the coefficient, it's 1.976 now compared to our 2.79. Again, we would expect these to be different when we have them both in the model, but what's problematic for us is these very low t-stats. We're saying these aren't significant, not when they're both in the model together. Independently, they had high R-squares, but we include them both in the model, not the case. Let's look at our other data set. What we find most troubling is initially our estimate for repair hours, our coefficient, was negative 76. With our slightly modified data set, it becomes 234, positive. Our machine hours was 1.976, positive. Now when we change our data set slightly, it becomes negative 4.94. When we have a high degree of multicollinearity between data sets, in other words, again, these data sets were basically identical, and I've designed it so our machine hours are basically telling the exact same story as repair hours. If we were to plot these two real quick with a scatter graph, we can see that they lie basically on a straight line. If we were to calculate the correlation matrix for them, we can see that these base variables are correlated. They're 0.99999% similar. So they're both trying to say or tell the same story. In one set, the repair hours tells a story where repair hours are negative and machine hours are positive coefficient. In the other, those are slightly distorted. And again, we get these vast swings or changes in our estimated coefficients and a suggestion that as long as repair hours are in the model, along with machine hours, neither variable is very significant. Independently, one variable at a time, both of them are highly significant and nearly identical in their R-squares, and we would expect that because they were what? Almost perfectly correlated. And again, these were highly contrived examples. Let's take a look at this a little closer with respect to, say, SAT scores and GPA. We often want to predict how well a student will do in college, and that could be performance in GPA that you earn at Millersville University. And things that might predict that would perhaps be your high school GPA or your SAT score. Now, if we look at these two variables independently, the GPA score has a 90% R-square. The SAT score explains 72% of the variability of how you do at Millersville. And again, these are just made-up data. And we can look at the slope coefficients. But what do we know about GPA and SAT? Will these two variables do much when we include both of them in an equation together? Because generally, not always the case, these two things measure similar things. Someone with a high school GPA, we would expect them to earn a decent SAT. Someone with a low high school GPA probably has a more challenge scoring well on the SAT. So these variables sort of are explaining somewhat the same information. Again, taken by themselves, we would probably say high school GPA, again based on our data set, is doing a better job at explaining our performance at Millersville. Let's look at our data for these two included both in one model. So we've got a multiple linear regression model. R-square, 91.2%, and again, it's going to be higher than the high school GPA by itself whenever we add another variable. Even if it doesn't provide any real beneficial information, we said our R-square will go up. So let's take a look at these. Let's look at our coefficients. Both of them are positive, which is what we would expect. In other words, the better you do with your high school GPA, the better we would expect you to do at Millersville. If we look at the standard errors for these two variables, though, and the t-stats, what do we observe? With both variables in the model, high school GPA has a t-stat of 6.19. So in other words, we were saying that our best estimate of the relationship is 0.861. How far away would we have to get to that null hypothesis that the real coefficient is 0? We'd have to go 6 standard deviations away. What's the probability that this is really 0, that there's no relationship between high school GPA and Millersville GPA? It's basically 0. However, what happens when we look at our SAT? By itself, I think our SAT was explaining 75% of the variability in Millersville performance. But once we add SAT in, along with high school GPA, we find the SAT doesn't have much explanatory power. We get an estimated coefficient of 0.001, standard error of 0.001, which basically says that this is less than 1 standard deviation away from, 0 is basically 1 standard deviation away from this estimate. The probability that there really is a relationship between SAT score and how you do at Millersville, again, important. Once we've already taken into account high school GPA, very, very slim. it just doesn't add much to our model. And again, one of the reasons is there's a fair degree of multicolinearity between these two variables. Both variables are trying to tell us a similar story. And once we listen to the story told by high school GPA, SAT scores don't add much in explaining how you're going to do at Millersville. Perhaps better variables to include along with high school GPA or SAT might be things like choice of major at Millersville. It might be the number of hours you spend working while you're attending school. It might be a variable that captures whether you're involved in sports. So there are other data points that might explain performance at Millersville that aren't trying to tell that same story as high school GPA and SAT. Both of them are trying to explain the same thing. What this basically means is whenever you're taking a look at more than one variable, you're going to want to be very careful to make sure that there's not a high degree of correlation between them. Typically, it's only when we have correlation between variables of more than 90% do we have a problem with multicolinearity. If I look at a scatter graph of this data, it's suggesting that there is a pretty strong positive correlation between the two. If I use Excel's data analysis tool and in particular looked at our correlation between the two variables, input range, here's my input range. Where do I want to put it? Let's just put it down here on my worksheet somewhere. 86%, it's getting near that area where both of them are trying to explain the same thing. I don't know that we have a problem with multicolinearity, but certainly looking at our regression output, once we have included high school GPA in our model, we don't have much benefit from including SAT scores as well. We should look for an alternative variable. And this sort of brings us to the next thing. We're going to take a look at estimating electric cost using a larger data set. And we're going to take and walk through a backwards stepwise method to eliminate variables.